Now, as Jim Cowie makes his way to the podium, I thought I'd put up the election page here so people know where to vote. It's that thing in the middle that says vote here. If you don't know how to get to it, there's only a half hour left or a little less to get your votes in. And FYI, if you've already voted, had second thoughts, you can change. That's what Betty let me know yesterday, is that you can keep finalizing your votes right up until the last minute. So vote early and literally vote often. So next we have Jim Cowie from Renesys giving a talk on who are those pesky Anycasters. And without further ado, here's Jim.
Thank you, sir. Where's the clicker? Here we go. All right. Hey, everybody. As you probably know, if you know me or if you know of me, I'm not any of the three people on this slide. I'm not Doug Midori, our senior analyst, who you met 2 NANOGs ago at the Sandy panel. And I'm certainly not Chris Cook or Kevin Miao, who were 2 really talented interns, actually, who came to Renesys. Every year we attract a few people, undergraduates, who want a shot at the data set, and they want to crawl through it and roll around in it like Scrooge McDuck. And I really like that, because after they've seen that data, it gives them some perspective on whether they want to go to graduate school and deal with synthetic data. Of course, we'd rather have them come to industry and deal with real data. We had Chris Cook from Bucknell, and we had Kevin Miao from Dartmouth. And sort of a best case outcome, Kevin has actually elected to join us as an engineer. This is a project that they took on. Typically, the interns will get something interesting that nobody else can find the time to get to. And so these are often really good little projects. In this particular case, we really wanted to understand who's doing Anycast. I mean, Anycast is old. Anycast is the typical thing that you do when you want a single service to be available at a consistent IP address, but you want to distribute it typically globally, right? It is not an entirely sophisticated thing to do. It's like, if you were building your own rustic wood furniture and you wanted to take a long time, like Akamai did, to build a very sophisticated global infrastructure, you build an entire wood shop with sophisticated tools. If you just wanted to build a couple pieces of furniture, you might go to the garage and get out the rusty chainsaw and fire it up. Anycast is kind of the rusty chainsaw of global load balancing. It functions. It certainly will improve latencies for many people. It may even improve reliability for some people. But then it has its share of mysteries, which we'll look into. People do use it still. They've never stopped using it. Consistently for content delivery, increasingly for DDoS protection, and of course for DNS, because it works really well with things that tend to be very stateless and UDP based. So rather than think about Anycast in particular, what these guys were doing is taking a look at what science it would take to understand what there is of Anycast, who's using it. One of the things about a dull chainsaw is that it actually becomes very difficult often to understand exactly why you get the furniture output that you get from the chainsaw. And you'll see here that we actually did some fairly exhaustive analysis to try to figure out when things are actually Anycasted. And some things are not 100% Anycasted, they are maybe partially Anycasted. So we used a combination of routing data and traceroute latency data. And together, we wanted to come up with a score. How much Anycasted is a given prefix? Perfect Anycasting maybe being a 1, perfect unicasting being a 0. And we'll just take a look, start at the top, work our way down and figure out where we think the threshold lies for what we think of collectively as Anycasting. So why would you do this at all? Well, at Renesys specifically, we really need things to be geolocated well. We're doing a lot of analysis where we roll up statistics about stability and performance in terms of geolocated regions. So we'd really like to know where things are. The problem with Anycast is that it really, by its nature, it causes IP addresses to be non-local. It smears them out like a wave function around the planet. So where is Google's Quad 8? Who do you believe? If you ask all of the various geolocation services that are out there, they'll tell you vaguely United States-like things, but some of them, they have very different ideas about where it is, legitimately, because they're all seeing different instances of it. It is in many places. Anycast is used quite a lot. Sometimes the promises and the realities may be hard to line up. Does it optimize routing? No. You'll get often optimal results, but you can't really tell if it's optimal or not. Does it minimize transaction latency? It certainly does for many people, and then you'll find people for whom it does not. Does it use the closest DNS server? Well, yeah, that's what it does. In some sense, it does, but they don't tell you in the asterisk at the bottom that it tells you the closest DNS server in some very high-dimensional metric space that you can envision, and it's not geographic, and it's not simple connectivity. In particular, we worry about the geolocation of infrastructure IPs. I think you'll have found out if you do geolocation that if you want to go out and figure out where things are, you can buy really pretty good data for places that are economically valuable to understand, like the eyeballs, the edge, the places you're serving ads. People have gone to a lot of trouble to get those geolocations to work. The infrastructure, less so. And so this is one of those categories where we had a project on the shelf to really go in, try to figure out where everything is, if in fact it has a place. And this is a category of things that kind of don't have a place. So here's one technique we used. Simple. Take a look at the BGP routing. Here's a typical /24. Most of the Anycasted prefixes turn out to be /24s. That's kind of an idiom. This, I think, is the /24 that hosts nic.br. And they have chosen to Anycast it around a little bit to make it available from places you'd expect, some places you wouldn't. So we go into each prefix in the full table. We take a look at the transit tree, iteratively, all the transit providers up to peering. And we try to figure out how many domestic providers there are in there and how many countries they represent. And if you've got a lot of discrete countries in there, then we start to feel like we might be looking at something that has been Anycast. And you can see here that they've got Peruvian, Chilean, Austrian, South Korean ASs in a transit relationship upstream of the Brazilian AS, which is the putative origin of this thing. Domestic provider, of course, is itself kind of a lie, because how can you tell where an AS actually is? We use a bald-faced cutoff. We just say, in this case, let's say 90%. If 90% of the prefixes you transit come from one country, we put you in that country. Okay, rough and ready kind of a rule. And what we'll take a look at is, well, there are a couple of exceptions, first of all. There are lots of cases where countries are kind of joined at the hip for historical, economic, fiber reasons. Russia and Kazakhstan, right? Lots of Kazakh transit through Russia. Papua New Guinea drinks internet from a soda straw out of Australia. I didn't put Canada and the US on the slide because that would be rude to the Canadians. Sorry. Satellite providers, where the hell are they? Nobody knows. They're everywhere, right? They're in orbit. Satgate, Eutelsat, these guys serve a zillion different countries all at once. It makes them what they are. That we can tell from latency data, but just from looking at the routing data, this is what it looks like. So here's some examples. These are some prefixes that bubble to the top of this particular metric that the interns came up with. SoundCloud, right at the top. You want to distribute your sound. My son loves SoundCloud. Everybody loves SoundCloud. It is all over the place. Indonesia, Netherlands, Russia, South Africa, US. Everybody loves SoundCloud. And so this is heavily Anycasted, and that's visible just from the BGP data alone without going any farther. Some of these are a little more mysterious. TUAT is an educational services provider. The K-root, of course, Anycasted. I don't know who Tatiana Alexandrovna Zvyankova is, but she does have an Anycasted /24. The Chilean NIC, and so forth. So, you've kind of squeezed all you can get out, and you're not getting a complete picture of Anycasting from BGP routing. Where do you go next? Well, we went to latency, and these guys came up with a second metric. We have, as you've seen before, this is our map of the 110 odd places around the world where we measure to every prefix that we can measure to using ping and trace route around the clock, trying to figure out what the latencies are between our collectors and everything. And when we pour that in, we start to be able to do some sort of simple metrics. Here's my favorite. Geo-inconsistency, the non-local nature of an IP address. If I take two collectors, and they both measure to the quote-unquote same IP, and they both get an answer, and the sum of those answers is less than the actual light speed distance between the 2 points I measured from, then something's up, okay? You know at that point that you're talking to two individual Anycasted services at the same IP, but it's not the same IP. It's in two different physical places. So here we've got 30 milliseconds to the target from one, 40 milliseconds to the other, but it's 100 milliseconds between. Well, it can't be. Now, there's lots of noise in traceroute measurement. So again, we're talking about likelihoods. But here's a tool that they cooked up called min latency. We took a look at Google's 8888 public DNS. And you can see that you can get there in 0 milliseconds from Sydney and 1 from Hong Kong. Go down the list. 2 milliseconds from Frankfurt, 5 from Amsterdam, on down the list. And you can see that that curve goes up very slowly, which means this is an Anycasted prefix, an Anycasted address. But of course, it's not perfectly Anycast because nobody can be everywhere. And more importantly, nobody can truly peer with everyone. And so there are always going to be people at the end of this curve that have very high latencies, even to something that is well Anycast. So here's what we did, or here's what they did. I just take credit for it. They take all the pairs of our observation points, and they say, well, how many observation pairs are there? What fraction of those? In other words, if I took 2 of our collection points at random, what are the odds that they would violate that triangle of latency? Call that inconsistency. Well, they built the tool to do that too. For Hong Kong, 1 millisecond to this target, Sydney 0, 72 milliseconds theoretical between Hong Kong and Sydney, it's inconsistent. Okay? So we went through, we found potentially 2,600, over 2,600 geo-inconsistent pairs on a day out of 6,200. That's a really good sign that that's Anycasted, and that's a kind of a cheat because we knew that was Anycasted, right? Google's Anycasting their public DNS. And it gives you a score, more importantly, that you can look at over time. So you can see how well are people Anycasting what they're trying to Anycast. And there's kind of a noisy signal, because remember, it's not just about geography, it's also about selected routes. And so it bobbles around a little bit over time. Here you can see both of the public DNS IPs, 8888 and 8844. And look what happens at the end. And here I'm going to have to ask for some help because I truly don't understand what happened here. Sometime in the middle of September, the degree of Anycastedness for Google's public DNS slipped. So here's one of them, 8888. And in particular, these are latencies. These are raw collector to 8888 measurements from about 6 of our South American traceroute servers. And spread around the continent, you can see that everything's kind of fine and flat, going all the way through 2013 until this event. At that point, the latencies, which had been as good as 0 for Sao Paulo, leap up to 125 plus milliseconds. If you look at 8844, you see exactly the same thing, except it starts 4 days earlier. So it's a similar, related, but not identical event. September 12th. So what happened? Well, we don't know, right? Part of the with Anycasting as a global technique is that it deliberately obscures the operational details of why things happen the way they do. The fact that you have to go in and write tools to do data mining and extract what's going on is a sign that maybe there's a problem with the technique in some cases. We don't know what happened at Google. We don't know. I'll show you in a second. There's a new hop that comes in to the trace routes. Trace routes from South America seem to follow the same path locally and then head to California. Here's a trace, for example. You can see on the left is before, goes 9 milliseconds, 9 milliseconds, 10 milliseconds, and we're done. On the right, 9 milliseconds, 16, Same 72.14 or /16. And then we're in California after 137 milliseconds, and then we're done. So that's the diff. Now, that's not to say that Anycast should not be relied on as a technique. It really does work when it works. Here's an example, right? Here's Hong Kong to the Google public DNS in 2013. You can see that previously the best route from our Hong Kong measurement point was 150 milliseconds. Here on the left, I won't bother pointing. And then you can see, wow, it falls right to 0 as soon as they turn that on. From Manila to Google, you see it stair-step down, boom, 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 and they end up with like 38 milliseconds, whereas it had been close to 100. That's a very substantial improvement. Okay, so that's Anycast on a global scale, which is how we all think of Anycast, right? I want it to be on every continent. I want a representative of my service on every continent. You can also use this technique to drill in a little more. You can look at things that have been Anycast over small areas. Here we see one where I trace to this particular IP, and it's 1 millisecond from Kiev, and it's 1 millisecond from Moscow. And Moscow and Kiev are 7 milliseconds apart. So in fact, this has been locally, regionally Anycast in Russia and the Ukraine by sports.ru. That's cutting it pretty thin. Perhaps a more realistic example is Osaka to Hong Kong, which is 26 milliseconds. And the numbers from those two targets, from those two collectors to this target, give 12 and 2, 12 and 3. In this case, this particular /24, that's Osaka, Hong Kong, we're noticing it is Baidu.hk. And that's also been MOASed. So, wherever you have one thing, you have potentially the other. Anycasting often looks like BGP hijacking. It's one of the reasons why we wanted somebody to dig into this, because it is an anomaly that needs to be rejected when you are building filters to look for real BGP hijackings that mean something. This one is innocent, right? It's quietly being Anycast over a small area. It's also being multiply originated by, in this case, 2 Baidu ASs, the Japan one and the Beijing one. If you take a look at who's Anycasting out there, you kind of see the expected cast of characters. This is not exhaustive. There are hundreds of them, but this is the top dozen by prefix count. Ultra DNS, you've got Edgecast, you've got Cloudflare, Prolexic, the guy's doing DDoS protection, as you would pretty much expect. And a lot of the big content guys. Google does a lot. Akamai does a wee bit. Yandex actually does some in Russia. Take a look at this. This is actually a plot worth studying for a second. This is how to think about the degree of Anycasting. So Anycasting is not like a light switch. I turn it on, it's Anycasted, it's perfect. I turn it off, it's unicasted. Anycasting is an optimization process where you're trying to get content closer to people, and you're never going to succeed all the way. So what we have here on the x-axis is all of our collectors, 110 some, sorted in increasing order of latency to these targets. And on the y-axis, you have the round-trip latencies. So a good result here would be one that starts flat and stays low. You want this to go right across from my best collector to my worst collector without significantly lifting off into high latency. And if you take a look, you see that Google really has the best coverage in the sense that that line is low and stays flat. It hugs the ground. You can see others. LRoot here does a good job. BRoot is not, right, Anycast. And so you can see that almost as a control, it comes up and over the top. It's in a good central location, so it doesn't have extraordinarily high latencies from anywhere, but the flat majority part of the curve is still around 180 to 200 milliseconds, and it too goes up at the end. For reasons, sports.ru is sort of in the orange there. They go up at the end, right, because they're only optimizing for local market, so I'm going to have a lot of collectors that don't really have much of an optimized look at sports.ru. And Microsoft, for unexplained reasons, goes right up at the end. There are some places on Earth that just have a hard time getting to the Microsoft Anycasted stuff. I think basically this, you'll take a look at this later. This summarizes some of the statistics. It's interesting as a control to compare B and L. L is interesting. This is, the way to think about this is how reliably can I get the benefits of my anycasting? LRoot is, old, it's studied, it's well anycasted. Here's a beautiful trace route from a collector in Los Angeles to the LRoot. Starts right off in Los Angeles, and in 0.4 milliseconds later, I'm there. I'm probably in the same building. I'm probably in the same aisle, it goes, boom, you're there. That's as good as it gets. That's what you want to see everywhere. Now, it doesn't always work that way. Here's one which, you'd be hard-pressed to read it from the back of the room. Let me go through it. Same deal. I'm trying to get to LRoot. I'm in Los Angeles. I'm in Cogent. I go Los Angeles, Houston, Atlanta. At this point, I go, wait, you're taking me across the country. Washington, New York, Boston. Whoa, what's up here? Liverpool, Manchester, Glasgow, Edinburgh, Dundee. 152 milliseconds. Why the hell am I going to LRoot in Dundee from Los Angeles? It's a mystery, right? The paths really do matter. So to summarize basically their findings, they found almost 600 of these prefixes globally. The vast majority are /24s, that's the idiom. The larger ones, of course, couldn't have any casted parts. People are not always anycasting, I guess, exactly according to what's publicly routed. The big ones, the things that are bigger than /24s include /22 from 1&1. China Unicom has a 21. Cable and wireless has an entire /16 that appears to be anycasted. Pretty interesting. So is this a major thing that you should think about? No. I mean, if you know about anycasting and if your business requires anycasting, you're probably already using anycasting and you don't care because you're getting your money's worth out of it. If you're thinking about using Anycast, you need to recognize that this is something that needs to be studied and modeled to figure out why it's doing what it's doing and when it's not delivering what it's delivering. It's funny that there are about 600 of these, 600 prefixes, and that's been the case for years. There's kind of a stable pool of people who do this. And it doesn't seem to be really growing, which I guess is good. It would be unusual if that took off as a trend. I think I did a presentation with Odd Tunderwood a while back where we thought this might actually take off as a solution for IPv4 exhaustion, where two organizations on opposite sides of the planet could kind of come to an agreement that their audiences were disjoint and therefore they could just both use the same /24. And that would be almost indistinguishable from true Anycast. But we haven't seen it yet. So unicast hosting, you get what you want, you know what you're getting, it's easy to measure. Anycast hosting, it's pretty simple. It often works. It's really hard to see what's happening in the tail. You really have to look from everywhere that you might conceivably have somebody who wants to touch your service. You really have to pick your markets and providers very carefully. And you really do have to go through and take a look at the paths from your critical customers to your Anycasted services, just to make sure that they're not going to Scotland. So thank you very much. Questions? Yes.
Hi, Joe Abley, ICANN LRoot operator.
Why is it in Scotland?
So very briefly, our deployment model for L is if somebody wants to host a box, we pretty much say yes. And in this case, Scotland Online in Dundee wanted to host a box. They use Cogent as a transit provider. Cogent are probably cheaper than all their other transit providers, so the traffic tends to go that way. We don't have any boxes in Cogent. But one thing I would point out with LRoot specifically, there are 13 root servers. And in particular, there's a C root, which is Anycast just inside Cogent's network. Mm-hmm. So in terms of stability of the services as a whole for the root system, we don't see this as a problem, but we see the local optimizations as more important.
Cool, nice observation. Anyone else? Yeah, oh, one more. Sure.
Regarding the hijacking analysis,
Mm-hmm.
is it more suspicious when an Anycast operator, or, I mean, does it look more like hijacking when an Anycast operator Anycasts from more than one AS?
It's hard, right? If you bring up the traditional origin for that prefix with a brand new novel transit provider in a weird country, I have a hard time telling whether you meant to do that or whether you're just putting the official origin in the path to blind that guy to the BGP hijack. Right? This is Mr. Capella at the mic has the original word on this, but does it make sense?
Hi, Jim. Dwayne Wessels from VeriSign. Sorry if I missed this, but could you say a little bit more about the source of the data? Did you test like every prefix in a routing table, or what was your list of prefixes to look at?
Yes. We used the whole routing table, and we used all the measurements we had to all of them.
Okay.
And we basically pulled the ones out at the top that looked like they're coming out with the strongest Anycast signal. And as you can see, some of them have pretty weak Anycast signals. And then the vast majority, 99% of the table, is just unicast.
So we're talking about 600 out of
400, 400,000.
Okay.
It's a full table.
How long does it take to do that kind of analysis? If it's not a secret.
If I did the work, I would tell you. I'm just taking credit for it.
Thanks.
Sure.
Anton Capel, standing in for Alex Underwood.
Very good.
Not in intellect anyway. So, thank you. We're working on it bit by bit. So Jim, say I was gambling and I was sending out pings as my bets.
Right.
How many do I have to throw out to get some certainty that's the lowest response time? I'm just curious, given you've done this presumably to a bunch of stuff within each prefix a lot.
Right.
Like, how fast does that ascend my likelihood to get a bet right as the lowest, say, 3 nines at a time? Just generally speaking. And this is different across the distribution of prefixes in an appreciable way.
Absolutely. The critical slide there, I'm down to like 28 seconds, so I won't roll back to it. But take a look at the Prezzo. There's a slide where we go to various targets and you look at the cumulative distribution of latency from the best to the worst. And you'll see that in general, that's a really flat curve. It reaches a consistent central value very quickly, which means that if I had to guess, maybe pick, if I had 110 and I picked 20, I could probably come with very good confidence and say, I found the middle. The odds that I would get, all of them at the tails of that curve would be pretty small. Sorry, waving my hands there. It's math. All right, thank you very much.